All right, welcome everyone. Chromium C++ 201 Part 2. Peter, floor is yours.
All right, welcome to another exciting episode of Chromium C++ 201. If you joined us for the first episode, then you have some idea of what this hour is going to be about. If not, then basically the very short summary is I will talk about pieces of C++ that are relevant to Chromium developers and probably should be known by everybody, but aren't necessarily the kinds of things that you learn immediately when learning C++ or when joining the team. So maybe useful to have a refresher or just brush up on all the sharp edges that you can run into. So there's a Go link on here, go/chromiumcpp-2. You are totally welcome to go to that either during or after my talk. At the very end of the talk, there's going to be some assignments for learning. As I said last time, I think these are really valuable because I think if somebody just talks at you, then it kind of goes in one ear and out the other. And if you really want to learn something, it's helpful to do it. So the assignments are designed to give you a little bit of practice in putting some of these things into use, cleaning up our code base a little bit. So we will get to that at the end. What else is in this talk? Today we're going to cover lambdas, base bind and base callback, const and constexper. And this is jammed as full as a turducken, so I'm going to move pretty quickly. I am reading the chat, so feel free to ask questions in chat or to just unmute and interrupt and yell at me. Hopefully I don't get too distracted this time. I don't have house cleaners here, so away we go. So lambdas. What is a lambda and why do we want to do it? The idea of a lambda is to give you some convenient sugar to do local inline functionality. So wouldn't it be nice if you were back in the days before C++ 11 and you were trying to use one of the cool things in the algorithm header and you could just kind of inline your predicate function right into the call like this. This is pseudocode, it doesn't actually work, but you can kind of get an idea that here we're just trying to very quickly check some bits on our child object. And this would have been very nice. Unfortunately, back in the days of pre-C++ 11, we had to write whole functors and all sorts of awfulness just to be able to use algorithm, which is a big part of why nobody used algorithm. So lambdas exist to give you an easy way to do something that is almost this short. They look like this. Basically, they look exactly like a function, except that the function name is replaced by what's called this capture block. Other than that, they're the same. They have a little set of arguments in parentheses, and they have a body in curly braces. So we're going to talk a little bit about what goes into each of these things. Here's some sample valid lambdas. They look a little bit gobbledygooky at first, but pretty quickly, if you just learn to read the little brackets as unnamed function X or something, then it starts to make sense. The top one is the simplest possible lambda, the do nothing thing that takes void and returns void and has no body. It's totally valid lambda, you can do that. The next two are slightly less simple, but still fairly simple lambdas. I will talk in a minute about what the ampersand means and the other stuff in that capture block. I want to highlight here something that's interesting about lambdas, going along with their idea of being syntactic sugar. This is basically a way to do something really cool and convenient, and that is this auto J that's in the fourth lambda here. What is this? Because if you think about auto and functions, you know that you can't declare function arguments this way. You can't just have a function that takes an auto X. So why can you do it with lambdas? Well, with a lambda, this basically is going to mean that we're going to deduce the argument at each call site. So this works exactly like a template. And in fact, under the hood, the compiler is going to implement this with a template. One of the themes of lambdas is that really they boil down to longer constructs that you could do without a lambda. It's just shorthand to make life more convenient for you. So in this case, the shorthand is for give me a templated argument. And what this means is you can write a lambda that takes an auto, and then you can call it with, say, 3.14, and the compiler will say, okay, and deduce double for that. And then you could call it again and pass true, and the compiler will say, okay, and deduce bool for that. So you can call the same Lambda multiple times with different types for its arguments if you use auto. This is very snazzy and convenient in not common, but not totally unknown sets of cases. And even if you only call it once, auto just means do what you thought I meant. Yes, on chat, we mentioned leaving out the return type. So that's conveniently timed because Lambdas do actually have a return type. It's also normally deduced for you. So you notice that there's no like void or int or anything else in front of the brackets, but there is an optional trailing return type. So if you don't have a trailing return type, the compiler is going to try to deduce this. It's effectively the Lambda returns auto. In this case, this will work just fine. We have return 3.0 or return 4.0. Those are both doubles. So the compiler will say, yay, this is a Lambda that returns a double. And it will happily deduce that, and you will be great. But if we change the code so that one of our statements returns an int and one returns a double, then the compiler will be confused and will throw up its hands and say, I don't know what you meant to do. Help me. So we can fix this by specifying an explicit return type. You can also do this at any other time, even if the compiler would have deduced it, just because you want to, say, make it obvious to the reader or something like that. But this is how you specify the return type of a Lambda, is you use trailing return type syntax and you say, hey, I want to return a double here. And then the compiler will say, OK, and it will coerce the return 3 into a double for you. So that's the arguments and the return type, but probably the most interesting and the most confusing part for beginners of Lambdas is the capture block. So let's take a closer look at the capture block. Here's some sample code without a Lambda that has y in an outer scope and then x in an inner scope. And as people who know C++ at probably about a 101 level should expect, you can write x plus equals y. You can't write x plus equals z unless, of course, there's some kind of z outside of what I've written here, because the compiler will say, I don't know what z means, but it's happy to look within your local scope and your parent scope and so on up your ancestors to find x and y. This works exactly the same with a Lambda if you put a magic little ampersand inside the capture block. That basically means default capture by reference. And so it says, OK, take everything in the surrounding scope for the Lambda and mirror it into this Lambda scope by reference. And the net effect is pretty much the same as if you had just written a little squiggly brace and you had an actual inner scope inlined right there. So the x that you declare is going to be scoped locally to the Lambda. The y is going to be a reference to the y that's in the containing scope. And once again, the z is going to cause the compiler confusion because it has no idea what you mean. So if you use this, we have a Lambda whose body just increments y. You call the Lambda, now y is 2. You call it again, now y is 3. This works just like if the Lambda was just a block of code inlined right there that you repeatedly called. So default capture by reference is very short to write. It's a little bit cryptic because it's just this ampersand sitting alone. But if you kind of think ampersand means reference, all right, that makes some sense. And it's perhaps the most do what I meant kind of capture that you can do. Unfortunately, there's some downsides to this. And the downsides are what you would expect if you are used to getting burned by C++ pointers and references. Namely, it's really easy to blow your foot off with dangling ones. So imagine this code. This code says, hey, create a Lambda and then return it outside this function. Give it back to my caller as some callable object. Well, that's maybe a reasonable sort of a thing to do, except that in this case, the Lambda is doing default capture of something that is in the scope of the function. So as soon as I return outside the function, the Lambda now has a reference to a variable that's no longer in scope. We've created a dangling reference, and the compiler will happily compile this for you and not warn you about it. So this is an easy way to blow your foot off. And it's one reason why our style guide is not terribly happy about using default capture by reference. So you might say, OK, well, we can conveniently fix this by having something different. If you replace your ampersand with an equal sign, you get something called default capture by value. And this does all the same things. It pulls all the same variables into your Lambda scope, except that instead of being references, they're now shadows. They're copies of the variables in the outer side. This is just like what happens if you pass arguments into your Lambda function by value. So you get a y in your inner scope, you can increment it, it becomes 2 inside the scope of the Lambda, but because it's now shadowing the outer variable, from the perspective of outside callers, now nothing happens. Y equals 1 after calling your Lambda, y still equals 1 after calling it again. None of the changes to the inner variables are reflected outer. And if you do this with our previous dangling reference thing, this is safer because now when we return the Lambda, we no longer have a reference to an object that has gone away. We have a copy, and the copy is scoped to the body of the Lambda, so we're not going to have a dangling ref. Hooray, we have prevented all possible problems, and everybody should just use default capture by value everywhere, right? Well, not exactly. So it's common in C to pass pointers around, and unfortunately, as soon as you pass a pointer by value, you still have the ability to create dangling, in this case, pointers for yourself by simply dereferencing them. So I'm showing here an example that will once again blow your foot off of simply capturing a pointer by value and then dereferencing it inside the Lambda, and the pointer points to something that goes out of scope. Now, this is the sort of thing that you can do to yourself without Lambdas. There's nothing new about this kind of problem. You can do it with functions too, by like returning, a pointer to a local variable. The problem with Lambdas is that it's often easy to do this without realizing it because the Lambda seems to your brain to be locally scoped. And so you don't sort of think about the dangers of passing the Lambda outside the scope. We're going to talk a little bit more about this when I talk about base bind and base callback and a feature that they have there. But for now, I will simply say that default capture by value is not a panacea that solves all possible dangling things for you any more than functions can never return dangling pointers. There's also another problem, which is that default capture by value has performance issues if you happen to use some really huge object inside your Lambda. If you have a gigantic container that's 8 megabytes or something, or worse, like 8,000 megabytes, and you reference it inside the Lambda, you just copied a very big object, and the compiler will happily do this, and you will probably have some kind of performance issue. So to get around these, we have individual capture. So this is actually my personal preference. And the style guide recommends this in various cases. Should it be int star pointer y equals address of y? I'm reading the chat here. I'm now looking back. Yes, it should. That's an error on the slide. Thank you. I will fix that later. Okay. So this is my personal preference for what to do because this makes it very explicit what the body of your Lambda is capturing. And if you want to go add something to it later, then you need to add to the list. Of course, it's also inconvenient and verbose, so there are downsides to it. But with individual capture, you can explicitly say what variables you're capturing and exactly how you want to capture each of them. Here, I'm capturing X by reference and Y by value. Now, some of you might say, well, shouldn't there be an equal sign in front of the Y indicating like, oh, it's by value? And to that, I will say, I don't know. The language designers did it this way. Don't blame me. I probably would have put an equal sign there, but they're doing it a bit more like how function arguments are specified, where if you just say int Y, then it's a copy by value. So you can do something like this to be explicit, or you can do a combination of the above. And you can say, in this case, capture everything by reference except for X by value. Your capture blocks can get as long and detailed as you want. There is one thing that I haven't talked about, and that is capturing this. So if you are writing in the context of a class and you try to call member functions, you might get bitten by the fact that the compiler will give you cryptic error message saying that it can't find where your member functions are and it doesn't know how to call them. To which you say, like, but I'm in a class. And the problem is that you need to either explicitly or implicitly capture the this pointer. Now, this is unlikely to bite you if you do default captures, because default captures include capturing the this pointer. So this will just work. But if you're like me and you like to write explicit capture lists for everything that your Lambda talks about, then you will probably want to write the fourth line here where you say this, to mention that, hey, I'm capturing this, and that allows me to refer to any of the member functions and any of the member variables of my class. There's esoteric things about exactly how this gets captured by value or by reference and blah, blah, blah. And they change in C++ 17, and I'm totally not going to go into all that stuff because it's like 301 or higher level. Also, Richard mentions in the chat that equals the default capture by value is deprecated in C++ 20. But luckily for Chromium, we don't have to care about that because we're stuck in the past on C++ 14. And C++ 20 is doubtless like 53 years away for us. So I joke. I'm hoping actually that C++ 20 is like a year away. But until then, we are stuck with C++ 14. So this is the land that we are working with. There's lots more I could say about Lambdas, but in the interest of time, I'm going to move on, except for, are there any questions before we go on to base bind and base callback? Everybody was like, that's amazing.
Yeah, I wanted to sort of, I don't know if you touched a little bit on this, but this versus what the style guide says of this, like half of these slides are like hard yikes, don't do it, right? When it comes to style guide, is that something you're going to talk about later?
I'm not really going to talk about what the style guide says that you should do, other than saying, like, in general, the style guide recommends that you use Lambdas carefully and that you be careful about default capture of any type, especially default capture by reference. And there's more in the style guide. Go read the style guide. Everyone should know the style guide. Style guide, yay.
If you want to pass these around, they're std functions, right?
They will decay to a std function, if I recall correctly. A Lambda itself has a implementation-dependent type that is basically not exposed, which is why I had my thing that returned it be a templated type. And you can store it in a std function, but it's not itself directly a std function. We will also, for those of you who know what std function and std bind are, I'm going to give you advance warning that I used to have a slide in the bind and callback section that I've excised for time that talks about why doesn't Chromium use std bind and std function. Go ahead.
I was going to ask about the lifetime of the closure. If you say store one of these, pass it to another function, are you storing multiple copies of the closure or multiple references to the same closure?
My answer off the top of my head is my brain is not enough in that space to know off the top of my head. I would say in general in Chromium, we don't tend to pass Lambdas around. We tend to pass callbacks around. And that goes to our next section, which is bind and callback. So what's the goal of bind and callback? Well, in this case, this is not just syntactic sugar. This is actually about giving you some capabilities that otherwise you maybe don't have easy access to. So what we want is pretty much functionality as a first-class object. Those of you who've studied any functional programming will say, gosh, that sounds a lot like a functional language, to which I will say, yes. and also not going to talk about that very much. Those of you who haven't studied functional programming can ignore that and simply consider this idea of this pseudocode here, a button click handler that simply wants to set its state to I've been clicked and then call some block of functionality that the user provided that says, I've been clicked, do stuff. Now, C's answer to this was use function pointers. So we just pass in, some kind of click handler function pointer, and then you call through the function pointer and you're good. There are basically two drawbacks to this. One is that the syntax for function pointers is kind of icky. The other more important drawback is that function pointers are fairly restricted in terms of what they can do. You can't do what I'm going to get to in a few slides called partial application. You can't sort of bind things and store them for later. The thing you should take away is function pointers kind of get partway here, but not really the full way. I'm not really going to elaborate on why functions as first-class objects are nifty or desirable in most cases that they're used. That's kind of a topic for a programming languages class. So I will simply say we use them very commonly, and pretty much anybody working with almost any part of Chrome backend code needs to understand what a callback is and how you create one and execute it. So that is what we're going to go over. The first thing is simply, how do you make one of these? Well, you make a callback by calling one of the bind functions. There's two of them, bind once and bind repeating. They make a once callback and a repeating callback. Hooray! What the difference is, once callbacks are meant to run once, repeating callbacks are meant to run more than once. This is one of those, it does what it says on the tin type of things. Once you have such a callback, you can execute it by calling the run method. So here I have some kind of function. I bind it into a callback. We're going to get to in a second exactly what the syntax of this means. And then I call .run, and it's exactly like I just called the function with the arguments that I passed to it with bind. Now, you can pass any additional arguments that you need in case you didn't bind all of them. And again, I'll elaborate on that more in a few slides. So if I only bound, say, one of my two arguments, then I can pass the other one when I call run. Run basically takes an arbitrary number of arguments, and they make up the rest of the things after the ones you bound. So you can just think of it as bound arguments and then additional free arguments. In chat, Peter asks, std move once callback.run, when, why, etc. Let me get back to that. There's a better slide to answer that question on. Null callbacks. So what happens if you just sort of declare one of these callbacks? You don't produce it with bind, you just have one. What is that like? Well, there's a method on callback called isNull. And in this case, isNull is going to return true. Isnull is sort of the ground state for a callback. If you try to run an isNull callback, it will crash. You should think of callbacks a bit like function pointers in that dereferencing a null one is a crash. It's not a no-op. So there's a difference between the null callback and like the do nothing or no-op callback. Just like there's a difference between a null function pointer and a pointer to a function that does nothing. Handy trick, if you really wanted a callback that does nothing, there is a method to produce that for you called base do nothing. There's also a method called base null callback. These produce the no-op callback and the null callback, except that the reason why you would want to use them is they actually produce something that deduces the signature that it needs in most cases. So you don't have to worry about producing a callback that takes exactly the right number and type of arguments and, you know, returns void or whatever. Like, you don't have to declare any of that. You just pass do nothing and you get what you wanted. A callback that does nothing. Now, there's an asterisk there, which is there are cases it doesn't work, and there are ways to work around that, but I'm not going to go over them in this talk. I will simply say most of the time, do nothing or null callback is what you want. Now, Now that we've introduced the idea of a null callback, I can talk more about once callbacks and repeating callbacks. So if you run a repeating callback, it doesn't modify the repeating call. Well, that's probably too strong of a statement. You can run the repeating callback again, and you will still be okay. If you run the once callback will become null. So when you run it again, it will crash because it's now a null pointer. The way that you do this is actually on this slide. I lied about the syntax, and you can't just .run most once callbacks. Once callback run is a rValueRef qualified method, which means for those of you who watched my last talk, you need to have an rValue reference to your callback to call run on it. So this actually means that you need to std move the once callback before you run it in most cases. Now, going along with that, once callbacks are move only. So it doesn't really make any sense to pass a once callback around by const reference, because since you have a const reference, you can't modify it, and that means you can't call run on it, and you can't convert it to a non-const like rValueRef. Effectively, like you've neutered it, and you or anybody you call is never going to be able to do anything with it again. So when you're passing once callbacks around, you need to pass them by value and std move them. It turns out that passing repeating callbacks by value and std moving them is generally fine too. So in a lot of cases, we just pass all callbacks by value and std move them. And that's perfectly reasonable sort of thing to do. But it's especially important in the case of once callbacks, since const refs are useless. Jason asks in chat, the repeating in repeating callback means you plan to repeatedly call it, not that it has a timer that repeatedly runs it. Yes, that is correct. A repeating callback can be run repeatedly, but it does not say auto repeat for you. We have things like timer and something else, but it escapes me, that does that in base for you. So yes, the difference between once and repeating callback is mostly a matter of documenting for the reader what you plan to do, and then having the compiler help enforce that by forcing the once callback to become null after you ran it, so that you can't use it too many times. Partial applications. So this is one of the things I think is coolest about bind and callback. And this just means that you can bind any number of arguments up to the number that your function takes, and you will be fine. You can bind 0 arguments, you can bind 1 arg, you can bind 2 args. In this case, our function only takes 2 args. So if you attempt to bind 3 args, the compiler will yell at you, and it won't compile. That's good. We like that. And you can even bind partially incrementally. So you can take your callback and you can bind on top of the callback instead of binding like directly to the original core function. And this is very nifty, because what this means is that you can have some sort of pattern where like you iteratively collect pieces of data for your function to take over time. And each time you get one back, you bind it onto the end of the thing. And then when you're all done getting all the data, you take the resulting callback and you run it. And yes, this is very much sort of mentally a builder pattern way of invoking functions here. The only difference is that the order is fixed. So you have to bind them like in the order the function takes it, and not just however you might like. You can also call member functions. So in the case of lambdas, the way you do that is by capturing this. In the case of bind, the way you do that is by passing whatever the appropriate this pointer is as a first argument before all of the other arguments. So here I'm showing an example where we have some class type C, and we want to call some member function on it called func. So we simply bind to C:func, and we pass some kind of instance pointer as our this. And now when we run it, it's like we've called func on that pointer. So very much like calling non-member functions, just with one extra argument in here. That is all I have on bind and callback. Once again, there's more I could say, but we'll stop there for now. Let's see, questions. Peter says, does star myc, okay, so on this one, does star myc work and not base unretained myc if no weak pointer? I think you mean does amper myc work and not base unretained amper myc? Yeah, I think you, in this case, the compiler will actually yell at you if you did not wrap myc with a base unretained here. I've elided that. I will claim I elided it for clarity instead of just forgetting it. Other questions before we move on to const? Base callback is split because of documentation purposes. Were there any security motivations? I was not involved in deciding that once callback and repeating callback was a good split. So I'm going to say officially, I don't know. Unofficially, I don't think there were. I think this was more about, hey, it would be really good if we could understand like what this is supposed to do.
Also, like you could only use move arguments with once callback, right?
I don't know if that compiles. I mean, it sort of only makes sense with once callback, because what does it mean to move the argument in and then call it and then try to call it again? It might not compile, but honestly, I haven't tried it in a couple of years, so I don't remember what happens when you try to do it.
I thought I had seen this in the code, but I could be mistaken.
It compile with repeating callback, which is kind of nice.
Also, if it never gets called, does it get deallocated?
So the callback object is just like any other object in that it's sitting around and, you know, needs to be passed around either by, you know, move or value copy or whatever, and eventually it gets destroyed or leaked. So I guess I'm not sure how to answer that question. Using weak pointer, I can't bind a function that returns non-void. Can we provide a way to specify a default return value when the weak pointer is invalidated to work around this? Oh, for that question, I will simply say ask CXX. I know that's come up before. I'm sure people have thoughts with a capital T. Okay, I'm going to move on for time. Const, my favorite. Why do we care? One could argue we don't. You can write a code base that doesn't use const to qualify members or to qualify functions or variables and get pretty far, do pretty much everything you want and not really have problems. In particular, one reason we do not care about const is to somehow produce better optimizations. And a big reason for that is because the compiler, in a lot of cases, cannot actually assume that something you declare as const stays const because of the existence of const cast. So I write a const int, and then I cast away const later and assign to it, and boom, like it's no longer really const. Now, this is kind of a contrived example, but there are real world examples where you cast away const in ways that are both legal and irritating. So const in general is not so much about make my code more optimal. It really has other purposes, and I think the primary purpose of const is documentation. Much like with once and repeating callback, you're trying to give the reader information here. So if you put const on a function, what you're trying to say is, this method doesn't affect the visible state of the system, of this object in particular. And if you put a const on a variable, you're saying something like, this is syntactic sugar. It's a shorthand for this other computation that's either too long or I repeated it or something like that. So you can just think of it as this thing. Both of these are, ideally, when used well, going to reduce the amount of thinking that readers need to do in order to understand your code. Now, when used poorly, they're not going to achieve that end, and we'll get to that. There is a secondary purpose, and that is, again, just like with once and repeating callback, it does let the compiler catch you in certain kinds of error cases. So if you have a const method, then you are not allowed to do things that muck with the bits of that object, except in the case of mutable, which we'll go over. So that in some cases can help save you when somebody came along later and started to write something that had a naive bug in it, and the compiler said, hey, you can't do that. And they said, oh, good. I didn't mean to do that. Incidentally, on the optimization thing, Alan asked, can the compiler still optimize if you never actually change the const within a block? The answer is yes. Compilers are kind of smart, and they will do constant propagation. And in fact, even without the word const, they will sometimes realize, like, you never change the value of this variable, and so I'm going to optimize. So the real answer there is compilers try to be as smart as they can, but the use of const itself is not so much about giving the compiler more ammo as it is giving the reader more information. Const in interfaces, is our style guide against it? So for clarity, you mean like putting const on methods, saying like get blah, blah, blah const.
Yeah.
Our style guide is not against this. In fact, our style guide encourages this. And there's one specific case in Chromium, which I won't go too much into, but the content layer in particular long had a rule that said don't make any methods const qualified. That's been relaxed recently. So that rule is now like you can make methods const qualified in some cases. And then in the rest of Chrome, it's pretty much like this can be a good idea. And I will talk more in a second about when it's a good idea. The gold standard for const documentation in our code base is this file, which if you have a copy of the slides open is a link to this file, styleguide/c++/const.md. It's called useconst correctly, and it goes into a lot of this stuff in more detail than I'm going to go into it here. But the short summary is there are two types of constness, physical constness and logical constness. Physical constness basically says no bits in the object have changed. This is what the compiler can check for you. This is basically about how you implement constness. Logical constness is much more about the API design of what your contract is, because it's the subtly different statement. Nothing about the object's meaning or state has changed. And furthermore, and this is a little weirder, nothing is going to change like through the use of this method. So the situation here is I hand you a const reference or pointer to const to myself or some other object I care about. What I want to guarantee is you can't go mess with the state of that object. This second part is important in order to have that guarantee. And I will give an example of that in a little bit. So usually these are the same thing. In most cases, physical and logical constants are identical to each other. Here's an example where they are. We have a simple getter and a simple setter for an integer member variable. The getter is const, the setter is not. And this is kind of what you would expect because the bits and the meaning are changing at the same time. However, you can have both of the mismatch cases. The case where you have something that's logically const but not physically const is denoted with the keyword mutable. Mutable comes up the most often when you're doing something like caches. So something where under the hood you have an implementation detail that is helping you to be, say, more performant or more efficient or more whatever, but it's not changing the state of the object or its return values in any way that the users of the class care about. It really is just sort of something that stays inside the black box of the object. In that case, those things are mutable to tell the compiler these may have their bits change physically, even in cases where the method logically is marked const. Some people feel like mutable is the sign of some kind of flaw in your design. That's not the case. There's nothing wrong with mutable. Mutable is not a code smell. Mutable on like literally every member of the entire class may be a code smell, but mutable just in the abstract is totally fine, and it's appropriate for this case. Something that is physically const but not logically const is scary, because the compiler cannot catch you here, and this is a way to introduce time bombs into your system. So this is an example of that violation of the don't let my method give me back a handle to something that will let me screw with the object later case. So let's say that I have some kind of a tree object, and I have an accessor that returns the left child. Now, it's a const accessor because all I'm doing is just reading the left child and returning it, right? I'm not touching any of the bits on the object. I'm not changing its state. Very clearly, like, just calling this method doesn't change anything. So it seems like it can be logically const and physically const, so it's const. And we return a C star. But unfortunately, cases like this are usually ways to give you back foot guns. Because typically now, what I can do is I can call a const getParent method on that left child, get back a pointer to non-const on my original object, and mutate it. And now I've done like mutating things to something that I originally had like a const reference or a const pointer to. And this was the entire thing we were trying to avoid by using const to begin with. So it turns out to be surprisingly hard to find cases where it's actually safe to return like pointers to non-const, and you can never use them to mess yourself up. And so our style guide takes the easy way out and says, just don't do this. If you have a const method and it returns a non-const pointer, you did it wrong. Either make it pointer to const or remove the const on this thing, or make there be a pair of methods, one const and one non-const, you know, that access the object in the two different ways. So let's see. I was reading P-Boss's question, but I think the answer to your question, P-Boss, is no, that's not allowed. Not going to go into it. Handy trick. If you have to do this, you have like both const and non-const methods, and the methods are complicated, you can implement one in terms of the other. The syntax for this is super ugly. It looks like this. I don't expect anybody to remember this. I certainly don't remember it. I go look it up when I need to do it. What you really should take away from this slide is simply there is a way to do it. It's ugly, so don't do it all the time. Like in particular, don't do it when your implementation is literally just like return member var. This is going to be uglier than like just copying that into both methods. But it is out there, and you can find it in our docs if you need to. Now, I've been talking about const on functions. What about const on variables? Well, the answer to that is sort of use your judgment. So since I said that the primary purpose of const is documentation, what your goal is to make things more readable. If adding const makes it more readable on net, then do it. If it doesn't, then don't. Unfortunately, people disagree about what more readable means, and so you will probably have to argue with your code reviewer if the two of you don't see eye to eye. But you know, there are extremes that I think most cases, most people agree are probably like excessive use of const, like the one I'm showing here, const t star, const t. I mean, like the number of consts in this is large enough that I have to think for a long time about exactly which one each means and whether it's important, and like this is kind of scary. On the other hand, t star star is already starting to be scary to me. So maybe the problem here is that you have a t star star. I don't know. Remember that saying const exists can be useful syntactic sugar, but on the other hand, the more verbiage you have, the more people have to think about. And so my answer is just balance those, and then I run away rapidly. The last thing I will say about const is simply that constness is viral. If you've ever tried to introduce it or remove it from a particular API, you will know this, that it winds like vines all through kinds of places, and you have to work very hard. And therefore, you really should think about constness, especially on methods, as a matter of API design and not a matter of implementation. This is not about like, oh, my bits didn't change, so I can go make this const. This is about, think about the contracts that you're expressing with your APIs, and then like think, okay, so does calling this method change the state of my system or not? That's an API design question. Your implementation can then be made to match. So if you're saying that you somehow have to set or remove constness based on the low-level needs of the implementation of the method, then I claim that your contract is not sufficiently well specified, or is specified at the wrong level, and you should go back to the design drawing board on it. That might be too bold of a claim in all cases, but it's a good general heuristic. So questions on const before our last section? No, okay. Constexper. Now, constexper is not the same as const. It's also not the same as const, but for expressions. Constexper actually is sort of like what naively some people might have thought const was, and that is constexper pretty much is about writing more optimal code. In particular, constexper makes things available to the compiler to use them at compile time. So it says like, hey, this function can be used at compile time. This variable can be initialized at compile time. And when you mark the whole transitive closure of a bunch of stuff at constexper, the compiler does a bunch of that work for you at compile time, and your code magically becomes wonderful and all things are better, right? Well, no, not exactly, but we'll get to that. So constexper is not so much about documentation and readability. It really is about optimization. Here's how it looks in practice. We have a function, func1, that's marked as constexper by putting constexper in front of the whole thing. And then we have a variable x that's also marked as constexper, and it's initialized by calling a function. This is fine. You can do this. We also have a non-constexper function, and we try to initialize a variable, a constexper variable with it. That is bad. The compiler will yell at you. So you can think of this in some sense as constexper on functions marks the set of things that the compiler is allowed to use at compile time and that we can verify are actually safe to do at compile time. This is sort of a way of carving out a subset of stuff that we hope isn't going to hit the halting problem. And then its whole purpose eventually is to initialize various variables at compile time, which we then do by saying everything is constexper. Now, just because you can use it at compile time doesn't mean you have to use it at compile time. You can use it at runtime. So here's a case where we have func1 being constexper, and I'm using it in both a compile time and a runtime context. Func1 is called for x, and it's also called by func2 here. This is totally fine. There is, in fact, a C++20 keyword called const eval that means it's only at compile time, but we're not on C++20, as I noted earlier. So when should you use constexper? Well, on variables, you should basically always use it if you can. So in this case, if you have like a const GFX size, make it a constexper GFX size if it works. This will give the compiler like the ability to initialize it and use it at compile time. Now, maybe it could do that in some cases already, but generally like constexper can help things actually get size and speed benefits. And sort of the heuristic here is if you would name the variable kfoo, it probably can be constexper. And if you wouldn't, it probably can't. If you don't know when you would name a variable kfoo, then this won't help you, but I'm sorry, I tried. On functions, it's not always a win. It's a win for constructors and operators on literal-like types. And what I mean by that are things that behave kind of like literals, like time and time delta and point and size and rect and other things where there's like a quantity and a unit for that quantity and you're sticking it in something. Not something like a web contents. That's a complicated sort of abstract notion. It's not a literal-like thing, so it doesn't really make any sense to put constexper, constructors, and operators on it. And constructors and operators are really the methods that you want to annotate to begin with, because those are the things that you need in order to initialize variables. So you don't typically need to put constexper on literally every method of your object. The reason that I say that you shouldn't just blindly put it on everything, besides the fact that it kind of doesn't make sense in some cases, is that constexper functions are required to be inline, because the compiler has to see the definition of the function in order to actually compute it at compile time. And if you make everything constexper, what you've done is you've made everything inline. And that should trigger some uneasy feelings about code size. You know, am I blowing up my executable size by making literally every function an inline function? It turns out the answer is yes. It's very easy to blow up your code size by having too much stuff be constexper, and I've done it. There are some things on time delta that are not constexper for precisely this reason. So the real answer is go find your literal-like types, go find the constructors and operators, make them constexper, and then run a binary size comparison and make sure you didn't just blow out the world. What can you do in a constexper function? Well, you can do stuff like arithmetic and control flow. You can even call other constexper functions. But what you cannot do is you can't allocate memory, and you can't call non-constexper stuff. And it turns out non-constexper stuff covers a surprising amount of the STL, especially in C++ 14. So if you want to, I tried to find an example of like an STL function that was constexper, and I'm like, oh, well, clearly like countif should be constexper. Nope, C++ 20. Oh, well, what about vector size? Nope, C++ 20. Okay, fine, vector empty. Nope, C++ 20. So the answer to this is probably the methods that you want in the STL are not constexper yet, and maybe they will be in a future revision of the standard that we haven't gotten yet, like C++ 20. Some things like std round would be very useful to be constexper and are not constexper even in C++ 20. So the upshot of this is if you want to declare a literal as constexper because it's a k, foo, blah, 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 and it's declared const, go ahead and try for it. Just be aware of the code size increase when you're doing so. So questions on constexper before we go to assignments. Isn't the compiler allowed to make something non-constexper if it deems the inline not to be worth it? My answer is, in general, I don't trust compilers to make the worth it decision on inlining in the same way that we would make the worth it decision on inlining. It's very hard for the compiler to know like what the right trade-offs are for your program. And so often we will pass flags to the compiler like compile for speed, that the compiler will use like, okay, inline almost everything, almost all the time, and then that will blow up your executable. Max says, does PGO help? Probably. So this gets into the same questions that you have about, in general, should I make my method inline? And the answer is, it depends. This is why I just do it and then check what the binary size impact is. Other questions? We're almost out of time. All right, assignments. Yay, my favorite part. So hopefully these are mostly self-explanatory, but I'll just go through them very quickly. You can try doing any or all of these things. If you do, you are welcome to send code reviews to me, and I will review them. You're also welcome to send those code reviews to owners of the relevant areas. Try replacing a helper function that's only called by one other place with a lambda in that other place, modulo that this makes readability sense. Try replacing a short helper function that's only used in a bind call with a lambda right in line in the bind call. Usually this does make readability sense if the function is short. Try replacing some kind of bespoke do-nothing function or lambda that's been passed to bind with base do-nothing. Now, this might actually be hard for you to find because I've replaced a lot of these in the past, but I'm sure some still exist out there somewhere. Go through and find 5 very simple, logically const accessor functions that aren't currently const and make them const. This probably won't really help too much of anything, but it's easy to do. It's not wrong. Go for it. Slightly more difficult, take some functions that are physically but not logically const, like the signature that I'm showing here, and make them const correct, whatever that means in this case. And then finally, go through 5 files that have some compile time constants that are not marked const or only marked const and make them constexper instead, because constexper all the things. So if you want to do these, write them down or open the slide deck or something. If you don't want to do these, well, I'm a sign, not a cop. Any final notes or questions in our last 2 minutes, or should I let you go? Can you talk about constexper versus static constexper? No, because I don't really understand. I actually kind of have some of that question myself. I don't know which one is better in which cases. Lambdas are kind of slow to compile. That is good to know. I used to have a note on one of these slides that I then excised for time that basically said, we don't generally try to optimize for compile time, which is sadly true. In fact, we sort of de-optimize for compile time. I don't know. If you have 200 small lambdas in your file, it might be the case that you could have refactored into a much smaller number of helper functions. I don't know. Maybe not. Would have to look at it. Everybody's like, can you talk about this obscure thing? Yes.
Peter,
Go ahead, Roger.
Is it fair to say that constexper really just means sort of forcible inline, but it doesn't actually mean the compiler is going to do the work at compile time?
Technically, yes. The compiler is not required to do constexper things at compile time. In practice, it generally will do them at compile time. There's almost no benefit to not doing it at compile time.
So then what would be why would you then have to worry about code bloat? Because ultimately it should all just be done at compile time and you should be left with something that's a compile time constant. In theory, right? In theory.
So I'll say this and then we're out of time, so feel free to jump off. But you are thinking more of the const eval case of this is only used at compile time, but it's perfectly possible for the function to also be used at runtime. And in general, the compiler doesn't know because it doesn't know if this is exposed outside the translation unit. So, I mean, unless your method is, linkage-wise is definitely scoped so the compiler knows, it can only be referenced here, and then it can get rid of it, then you have to rely on PGO or something like that to clean up the otherwise emitted version. So yes, if you only use a method for compile time initializations and you never use it anywhere else, then you won't have to worry about code bloat. But if you use it for any other thing, then it can get inlined in other things and you can die.
But the one thing I don't understand yet about it is that isn't the compiler allowed? Why doesn't the compiler just say if it's inlined too much, I generate a runtime version of it?
A lot of problems here come down to C++'s compilation model, where you're sort of looking at things one source file at a time. And so inline too much might mean that you inlined it once each in 1 million source files. And it's very hard for the compiler to understand that that's a problem because it only sees each one at a time.
Interesting, but why is it then different from the advice is much different from, like, usually you don't annotate every function with either inline or no inline. Like you said, the compiler will automatically decide which is best. But this doesn't seem to work here, so that's why
the compiler actually doesn't generally decide to inline or not inline various things. Like generally, if you make something possible to inline, in most cases it will get inlined, and if you don't make it possible to inline, it won't get inlined. So the compiler, you can think of the compiler as fairly ignorant when it comes to understanding what it should do with inlining, which is fair because in most cases as programmers, we're not sure what the right thing to do is either. Like, it may seem on the face of it like inlining all of your std string operations makes sense, and then you look at the generated assembly and you say, maybe that didn't make sense. So, we're out of time. So I'm gonna call it since it's 11:02. But feel free to stick around on the call after the recording is done, and I will stay here for a few minutes because I don't have anything better to do. So thanks for listening.
Thank you.
Enjoy your day.